So I'm going to say hello, everyone, and welcome to this week's CES Online webinar. My name is Mariano Ramirez, and I'm going to moderate today's talk. But before we get started, I would like to thank to our sponsorship from the International Association of Sedimentologists, which allow us to offer all these resources free of charge. Please make sure and check out our website for more information on upcoming events and meetings, and notice that we have a change in these webinars for the coming month. Today's lecture is by Linda Hinauf from the Atmospheric, Oceanic and Earth Science Department in George Mason University in the Eastern United States. Linda received her bachelor degree in music in Princeton University, her master in geophysics in University of Texas at Austin, and her PhD from Johns Hopkins, right, Linda? Johns Hopkins.
Hopkins.
And her current research focuses on the analysis and modeling of cyclostratigraphy and deep-time sedimentological record of Earth science paleoclimatic, geophysical, and astronomical variations. She also coordinates these amazing cycloastro projects. Today, she's going to talk us about the promise of cyclostratigraphy to shed light on solar system and Earth-Moon dynamic through the geological time. So, Linda, the stage is all yours.
Thank you, Mariano. Thank you so much for providing me with this opportunity to talk about cyclostratigraphy and its power to shed light on the solar system and Earth-Moon dynamics through geological time as far back as cyclostratigraphy goes. So this research that I'm going to present to you today is part of an ongoing effort with 3 organized teams working independently in Paris. I see some Paris members here today. China, I also see that they're here today. And here in the US with the so-called Cycloastro project, which I have shown here on my slide. So let's get to it right away. I think we should review what has happened in cyclostratigraphy over the past decade. And this actually is reaping the rewards of decades of hard work on here, in the case of the Cenozoic record here, on ships, in the field, struggling with processing, correlation, biostratigraphy, magnetostratigraphy, and much, much more. And so shown here is the Dell 18O megasplice by de Vleeschouwer et al. In 2017, which joins together single unstacked records from end to end for the past 35 million years. So the detail on the lower left shows part of the early Pleistocene, and you can see all of the cycles that are associated with astronomical parameters, including the long eccentricity, capital E, the short eccentricity, the little e's, and the obliquities denoted by O's, and precession, the individual cycles denoted by P. And so on the lower right, you can see the spectrum of the entire record showing very strong eccentricity peaks at 405, 131, 124, 99, 41, and then all the way down here in the precession band, we had to boost the power to see the lines at 23.5, 22.2, 20, and 18.96. Now, this particular record was astronomically tuned to a multi-component target. And so one might say that it's somewhat contaminated by the tuning. So we're not sure how much of that is actually record, and some of it might actually be tuned noise. Nonetheless, it shows a very, based on the record here on the left, on the lower left, it shows strong evidence for having recorded astronomical cycles. This is from the mid-Cretaceous, the Aptian Albion, Fucoid marls from Italy, central Italy, and it's from the Piobico core that was drilled by Isabella Premoli Silva back in 1979, and it's still being worked on today. Here, this one is minimally tuned to 405,000 year cycles. You can see these cycles denoted here across the top. And it covers more than almost 24 million years. Although I have to tell you that the Aptian now has been recalibrated and is much shorter. And so this will have to be done all over again, at least for the Aptian. So again, you can see from the Amadeus segment, you can see a small portion here where we have multiple orders of cycles, these long ones being interpreted as 405,000 year cycles. Then we have 100,000 year cycles with little e, and occasionally we have obliquity that comes in, but it's not always there. And then the smallest cycles of all are precession cycles. So if you analyze the entire record, you get this spectrum on the right with 415,000 year cycles, 135, 141. And then again, we have to boost down here in the higher frequencies to show that now we're starting to see a shift in the peaks from that of the former of the Cenozoic, which is at 23.5 down to 18.96 to 22.54, going down to 18.46 and 17.8. These may be very important changes. And finally, I wanted to show you, one of the most remarkable records of all that's currently being reanalyzed again from the Triassic of the Newark series of Triassic age here in the eastern United States. It's continental and it ranges from lacustrine, deep lacustrine at the oldest part and into more an arid phase where it dries out every once in a while, and then a long phase at the top with persistent aridity affecting the basin here. So again, if you look down here between 220 and 221 million years ago, you can see these long-term cycles, which are interpreted as E cycles. They were discovered back in the 1920s by a geologist, by an astronomer and amateur geologist, McLaughlin, who mapped them out and was able to correlate them across New Jersey and eastern Pennsylvania. And within them, you can see these E cycles, and these are made up of these P cycles, these bundles of P cycles. And again, when you analyze the entire record, you can see very strong, these have been tuned only to these 405,000 year McLaughlin cycles. And so the success of the tuning is shown here with the 405,000 year, here's 125 and 95. And there's no obliquity in this particular record, although we do know that at the top of the series, there is obliquity in other proxies that have been collected since the 1990s. But down here, if you expand the Y scale in the precession band, again, you can see this strange looking 24.6 that we don't understand, but we also get 21 and 18 and 17. Again, a little bit shorter than the Cretaceous example we just looked at. Okay, so to summarize what we're seeing here, this shows an artificial spectrum of the Earth's astronomical parameters based on the Lascar 2004 series, just for the past 10 million years. So I'm safe, presumably, in the validity of this part of the solution. And this shows that the orbital eccentricity and the obliquity in the climatic precession has these is characterized by these lines that persist through the series that have specific periods. So if you look at E here, E is the 405,000 year, and it's actually a combination of these two frequencies, G2 and G5, and we're going to discuss what those are in a few minutes. And then the short eccentricity is all these E1, E2, 3, and 4, and these are all combinations of these other G's here. The obliquity, on the other hand, is a combination of this K, and we're going to talk about K. K is actually the precession rate of the Earth, and these are the S fundamental frequencies of the astronomical solution. And the climatic precession, these are all noted here, you can see all of these notated, are where the are characterized by 24, 22, 19, 18.9 thousand year lines. And there's another one down here, it's very small. And these derive from K plus a number of the different G's. So what I'm going to do next is talk about each of these, the origins of these different parameters. They're all modeled, and they have shown to be present in geological data. So this shows a diagram of the orbit of the Earth around the sun, and the various elements that are used to define the orbit and its motions. This is a diagram from Alberto Malinverno, and it's based largely on Jacques Lascar's diagrams of the same. So two complex variables are used to describe the orbital motion of a planet. In this case, I'm showing Earth. One tracks the orbital eccentricity and the longitude of perihelion, which indicates, the orbital eccentricity flexes a little bit, and then the perihelion moves. And so this is the eccentricity, and then the longitude of perihelion, and this can be framed as a sum of trigonometric terms with frequencies G sub j. I've noted J here because I here represents imaginary numbers. And then a second variable, the zeta variable, which tracks orbital inclination and the ascending node. So this and the inclination and ascending node, its rotation. And so this is given as a trigonometric series with the frequencies S sub j, and this runs from j equals 1 for the Lascar 2004 solutions, from 1 to 9, and each planet in succession from the sun is given its unique number. So Earth would be number 3, for example. So the solution is performed by direct integration, and then the G of I and S of I are estimated by frequency analysis. And the Lascar 2004 solution also shows us that for each of the planets, the frequencies themselves are not constant. They're not constant. So for example, this is today, and this goes backward in time, and they vary slightly. And so that's just the nature of the solution. And so this is the range over which each of these varies. You can see a couple of interesting, so this is for the G's on this side. These are for the S's on this side. Now we know at this point that the solution is accurate only back to about 40 million years ago. And so we can be pretty safe to compare cyclostratigraphic data with the Lascar solution back to 2004. I know that Jacques Lascar is working on new solutions that are going further back in time, and so we're waiting to see what that looks like. And also Richard Zeeby has been working to carry the solution back, and he seems to have carried it back to about 60 million years. But we still need to verify that with cyclostratigraphy. Anyway, so these are the G's and these are the S's, and there's no solution for S5 I think the invariable plane is somehow related to the inclination to the orbit of Jupiter. But Jacques will have to correct me when we're done. So, but these are the values that are given for in the past 5 million years or so for each of these. And so you can use these in combination with the precession rate to predict the periods of the climatic precession and the obliquity components in cyclostratigraphy. And then, of course, the differences among these will give you the eccentricity. Okay, so I want to turn now to the Earth-Moon system and talk first a little bit about the phenomenon of tidal dissipation. It was first proposed by the German philosopher, as far as I know, in 1754, when he wrote an essay for a competition, a science competition, which he did not win. But he was correct that the perpetual motion of the world ocean from east to west always contributes somewhat to the diminution of the axial rotation of the Earth. That was his conclusion. The guy who won the competition said that there was no change in the rotation of the Earth. So, and he turned out to be wrong. He was an Italian. Many apologies to all the Italians here. But if you look at the Earth from above the North Pole, and it's spinning in the counterclockwise direction, the moon is out here and it's revolving around the Earth also in the counterclockwise direction. And the moon raises a tidal bulge, but the tidal bulge does not complete its I want to say the full bulge response until the Earth has rotated a distance or an angular distance of delta beyond the Earth-Moon axis. So this results in the moon exerting a torque on the tidal bulge, and it's constant depending on where the bulge is and what it's doing, and imposes a braking mechanism on the Earth's rotation, braking as in slowing it down. And then the tidal bulge also exerts a torque on the moon, which then accelerates and recedes from the Earth. So this is from Monk, 1997, who tried to describe this in detail. So the other phenomenon is the one of the Earth's shape, its ellipticity, and actually the dynamical ellipticity also accounts for the mass distribution within the Earth, as well, which also is reflected in its shape outside of the Earth. And this is can also be visualized with the gravity, the global gravity of the Earth. And this is known as the Potsdam gravity potato. And here you can see there's Africa all around here. And this is United Kingdom, which is where this is being broadcast from. And there's a big positive out here and a low just right here in India. And so these have different origins, some shallow in the Earth and some deep in the Earth, and is of great interest to geophysicists working on the Earth's interior. But the dynamical ellipticity is just the difference between the polar and average equatorial moments of inertia normalized by the polar moment of inertia. And this is also important, and it itself is affected by the rotation rate of the Earth. I might just mention that it's dependent on the rotation rate of the Earth, as I said, and the mass redistribution on the Earth and within the Earth that involves also mantle convection. But it's thought to be less consequential compared with tidal dissipation over the long term. famous last words. All right, so this shows a summary of the geological evidence and models, both old and new, for the decreasing Earth rotation through geologic time. And it's shown with, on the y-axis is the hours per solar day, and this is the geologic time scale across the bottom. So the symbols indicate different types of geological evidence. There's probably, I know that there's more than what is shown here, but these are thought to be the most reliable of the geological materials. So for example, bivalves, corals, tidalites, they all provide a tidal signal. Bivalves and corals also, in addition to that, have an annual seasonal cycle, which is very important for determining the length of a year. Stromatolites, geologists who study, paleontologists who study stromatolites do not have any confidence in stromatolites. And brachiopods are also interesting and may give us information. I mean, they seem to give us good information here in the Phanerozoic already. And then there's this category called cyclostratigraphy, because cyclostratigraphy gives us information about length of day. And so there are different models for this. One of the early models, I can't really see here. Here we go. So we have 3 cyclostratigraphic data points that we can point to. And I will discuss these two further later in the talk. This one is from Lantink et al. It was just published a week ago about the Joffrey member. It was abandoned iron formation in Western Australia. And so they placed their length of day estimate at 16.9 hours per day. So the different models include the one that's a back extrapolation based on lunar laser ranging. It's okay for the first part of the geologic record, but then it becomes way too severe and unrealistic and reaches the Roche limit at which the moon actually back extrapolates back into the Earth by 1.5 to 2 million years ago. So that's not a realistic model beyond a certain point. There's another one that Polyatov, who did a small model, and it would be interesting to see if he wants to change this model and extend it in the future. The Bartlett and Stevenson model considers tidal dissipation with atmospheric resonance. So this is a very interesting model because as you go forward in time, he starts at about 4.4 billion years ago. As you go forward in time and length of day slows down, it reaches this point at 21 hours, which happens to be, if the day is 21 hours long, then it raises a thermal tide in the atmosphere, and it's just large enough to resonate with the lunar tidal torque that operates in the opposite direction. And so there's no forcing anymore, no net forcing, and so the day remains at 21 hours for an unknown amount of time, theoretically. And it may be pushed out of this stable pattern, perhaps by the snowball Earths. So that's a very interesting model to consider. And it was originally discussed by Zanla and Walker back in 1987, and then revived by Bartlett and Stevenson. Tyler 2021 considers Earth Q factor and ocean depth and comes up with these 3 models. And they stay at relatively high length of day all the way back to the beginning, to when the moon started. So those are also something to consider. Some of these data may follow that curve. And finally, most recently, just a month ago or so, Farhat et al. From the Paris group published this curve that is it is a curve that is divided into 3 parts based on what plate tectonics and the whole Earth system was doing. So, for example, back here, there was a global ocean. There were no continents. Then there was what they called a hemispherical Earth to represent the time at which plate tectonics was developing. And then in the Phanerozoic, another regime or phase called I can't remember the global the ocean. It was a continental ocean model. So this is when we have full plate tectonics. So there's 3 different regimes, and they are separated by different resonance patterns that tend to develop as a result of the changing ocean basins. So so far it looks, when you look at his paper, the data, including this one here, including all 3 cyclostratigraphic points here, seems to be a very accurate model. So we'll see how it plays out as we go further along and look at new data. Oh, okay. So the other thing to keep in mind is that there is an exchange of angular momentum between the slowing Earth and the Moon, which drifts away. So of course, when further back in time, it was closer to the Earth, and these are 4 trajectories provided by Webb et al. In 1982 to represent the fairly simple models: frequency-independent tidal torques for A, which gives enters the Roche limit way too soon, and B is one that imposes frequency-independent power dissipation, which is a little bit better, and then ocean model power dissipation, which is an ocean model seems to work with a lot of the data, and then D is ocean plus solid Earth power dissipation, and at least this particular calculation gives it a Roche limit that is older than the age of the Earth as we know it. This one may be the best one, although the data sort of line up in different places. And this is the Lascar back extrapolation model imposed on here just to show that it too is unrealistic for older ages. All right, so this is, so I want to move on and talk a little bit about the precession of the Earth. It's one of the hardest things to talk about, so we'll see how I do. But the Earth, first of all, the Earth is rotating, and it has a rotation axis that is tilted with respect to the normal of the ecliptic by 23.4 degrees at the moment, and it's changing daily and continuously. And so the Earth is rotating in a prograde or counterclockwise direction, and it's raising this this equatorial bulge, which is you can divide into 2 parts. One is symmetric around the ecliptic and the other is not. And so this causes a force differential between the 2 from the sun, moon, and other planets that are all acting in the ecliptic plane, basically. I mean, all the, the sun and the moon and all the planets are within a few degrees of the ecliptic of the orbital ecliptic. So the Earth is trying to right itself to bring this back to normal, but it can't because it's rotating, and so it precesses in the retrograde direction. A well-known model for the precession rate is shown here by K. And so K is what we have been talking about, combining with the G's and the S's to get the obliquity in the climatic precession periods. So this is This is the equation. So this is rotation rate. This is mean motion of the sun, the dynamical ellipticity. This is the eccentricity of the Earth's orbit, while this is the eccentricity of the lunar orbit. This is the inclination of the lunar orbit relative to the Earth. And so you can read all of these down here. One interesting thing to note here, something I didn't know for many years, because I was a geologist with poor training in geophysics, was that the rotation rate, while it's in the denominator, so for many years I was confused as to, well, if it's in the denominator, then it should be inversely related to the precession rate. But H is proportional to the rotation rate squared. In other words, when it rotates faster, when the Earth rotates faster, it gets flatter. So there's a flattening component to related to the rotation rate. So since it's a rotation rate squared, then this cancels out in the denominator, and so the precession rate is proportionate to the rotation rate itself in a indirect way. So so that explains why when you have faster rotation rate, you have a larger K. Okay, so let's come back to this again. So today we have an average K of about 50.476 arc seconds per year. And so to get okay, so if you add K to S6, which in a slide far before is also in arc seconds per year, you will get a arc seconds per year value. But then if you can convert it to period in years, if you just calculate how much time it takes to make the full circle. So that's how you get back to these values here. And so all of these values depend on this, and all of the S's and G's that are calculated for the most recent, I want to call it an epoch for the solution, although that may not be the right term. So so that's where all these come from. So you can see that the K is going to have an effect if it changes its rate. And so, of course, it's going to change its rate because the Earth's rotation rate is changing. So here, this is, again, I relied on Lascar to give us an idea, at least for his model, for the rotation rate back in the past, based on back calculation of present day conditions, what it would look like for the past 250 million years. And so today it's 50.475, that's about right. And back in the past, it's much faster. And so there's also another model that is sort of the same for this period of time that goes on back by Farhat et al. To 2022. And so that will be a very interesting K to refer to in the future. But I didn't have a chance to put it here. All right, so this has the effect, because the K gets faster, then the arc seconds per year gets faster, and so the periods get shorter. So this is obliquity periods for the 54, 41, 39, 29, 28 today, and then back 250 million years ago, according to the Lascar dissipation model. So if 41 was 41 here, 250 million years ago, it will be 31 to 33,000 years. And the 24 will be at 250 million years ago should be around 20.75 thousand years. So the question is, can we verify these changes with cyclostratigraphy? These are, we can model everything forever and never know whether we're right or not until we have some geological data. So cyclostratigraphy. So we have these bivalves you can find every once in a while, and you can maybe find a tidalite once every 1 billion years, and or more often, in the Carboniferous, for example. But it's difficult to find those fossils or tidalites that have recorded everything perfectly in order to get that information. So how can cyclostratigraphy take up the slack? So this is where we came up with these proof of concept studies. And the first one to do this was Myers and Malanverno. And they looked at 2 series, and we're going to look at those today. And then this was followed on by Zhu et al. 2022, our Chinese colleagues, and they just published a paper with 4 additional series. So all of the dates of these 4 different cyclostratigraphic sections are up here. And we're going to start with these 2 here, and we're going to go back and look at each one of these. And so this one here is from the Ocean Drilling Project, site 1262, and this is the core photograph. Here's the PETM. So this is above the PETM here. And if you analyze the A star color, which is the red versus green, it follows generally, it's a good proxy for iron concentration. And so this is what it looks like. It's unbelievable. It's one of the, it's just an unbelievable series. You can see the 400,000 year cycles. And then inside you can see the 100,000 year cycles. And then there's stuff inside of them. And when you apply this technique that I'll discuss shortly called time-op MCMC, it estimates the duration of 1,600 kiloyears, 1.6 million years. So this is a core. This is a core example. If you go to China, we're going to look at 3 Chinese formations. The Wutaping Formation is shown here. Here's some geologists for scale, and they have been able to determine all of these cycles. Here's the 400,000 year cycle and 100,000 year cycles within them. There's a big change in sedimentation rate right here. And right up here, sedimentation rates just decline to almost nothing. And this is the Permian-Triassic boundary. So as very important boundary, if there are astronomers here, it is it's the time of the most severe biotic extinctions that we had in the Phanerozoic. So this interval here is maybe a little further down in the series, but again, it shows these big cycles, and inside you can sort of see these others. So this is actually has been determined by time-op MC to be 1 million years long, and these are 400,000 year cycles, and you can see 100,000 year cycles inside them, and then stuff inside. And this is from the outcrop itself. So these outcrops are much more difficult to analyze. And this is also a marine carbonate. It's more on a deep platform environment, whereas this one up here in the Cenozoic is marine pelagic. This is the Pingliang Formation from the Ordovician. This is its outcrop here, and here's the biozones that are very helpful in helping us determine where we are exactly in time. And this is a magnetic susceptibility proxy measurement series, and magnetic susceptibility measures the total magnetic mineral content of the rock at each location, at each position. And this facies is basal marine, mixed carbonate siliciclastic, and the time up to MCMC technique estimated 800,000 years for this. So this is a little, so somewhere in here we should be able to see 400,000 years. I can see 100,000 year cycles, and they should be grouped into groups of 4. It's very hard to see in this one. So we'll see what happens when we apply time up MCMC. The Datang Paul formation is 655 million years old. This is an outcrop of it, but Bao et al. Analyzed a core and measured magnetic susceptibility again for magnetic mineral content. And this facies is it's related, it falls between 2 snowball Earths. It's a very unusual situation, and is a basal marine laminated siltstone shale series. And time opt MCMC estimates a duration of 700,000 years here. So I can sort of see maybe 700 or 800, 400,000 year cycles, maybe like this, 1, 2, 3, 4, maybe. It's hard to see by eye. We have to depend on time off MCMC and spectral analysis to really see the results. And finally, we're moving back into the Precambrian, further into the Precambrian. This is the second series that was analyzed by Myers and Malinverno, who developed the time opt MCMC methodology that I'm going to describe next. And so they analyzed this series from the Shamaling formation. It's the copper aluminum proxy and is thought to represent upwelling and productivity. And it's a deep marine basin. And it estimated this to be approximately 600,000 years long. So here's, I can sort of see a 400,000 year cycle, one, and then 100,000s inside with big, presumably precession cycles. And the oldest we looked at was the Dales Gorge member, previously analyzed by Rodriguez et al. 2019 visually. And Rodriguez et al. Published a grayscale scan that's shown here. And this is a proxy for iron, which is dark, versus chert, which is light, rhythms. And this is a superior type BIF and is thought to have been deposited on the outer shelf, maybe upper slope area. So it was not shallow and does not show much evidence, any evidence for exposure. And time up MCMC estimates a duration of 1,250 kiloyears. And this is also done using a core. This was done on the outcrop. So a mix of different types of strategies to collect the data. So the methodology, and we're coming down to the end of the talk, is Bayesian inversion time opt MCMC. So if you have read the Myers 2015 paper, he describes a method called time opt that links observations of climate precession, looks at the modulations of the climate precession, and links them to the orbital eccentricity band of the same series, and tries to and attempts to reconcile the sedimentation rate so that the two agree. And this is done to optimize K and the GI, because K plus G1, K plus G2 are the precession index frequencies. And they used Bayesian Markov chain Monte Carlo simulation to explore the data and the model space of this solution and to estimate uncertainties on the results. So for example, this is the Shamaling series. It's turned sideways here. And the interpretation is that the individual beds are precession index and that these are short eccentricity, and this is long eccentricity. And the optimization goes in and across a series of sedimentation rates and starting probabilities for the different parameters. And these all show that the best length of day, which results from K estimate, is 18.5 hours. And these are estimates for the short eccentricity cycles, which are somewhat interesting because they're not exactly what we thought it might be. And this is G2 minus G5, which is the 405,000. And these are the precession index, or the climatic precession periods that are estimated with a lot of overlap. So this result in particular, he doesn't have K in this particular display, but the length of day can be then converted to Earth-Moon distance with the principle of angular momentum conservation, and gives an Earth-Moon distance that plots here for 1.4 billion years ago. So about 340,000 kilometers. Today it's 384.4. So that's where this plots. And he did the same for the other Eocene series that we talked about, and estimated 383,000 kilometers. So this is where we started, and the next slide I transferred his results over to here, the Myers and Molinverno, and then Zhu et al. Zhu is a PhD student at Beijing and CUG, China University of Geosciences. He's just published this paper, and he analyzed these four series of these Chinese sections, and then this Australian section, the Dales Gorge, which I just showed you. And this is the result he gets in terms of Earth-Moon distance. And he adapted the BCron package in order to estimate these uncertainties. So it looks like all the way up to here, to the to 1.4 billion years ago, it follows it sort of follows the so-called ocean model, and then something happens and it changes direction and slows down quite a bit, the Earth-Moon distance change. So this is going to be calculated again because there's new geochronology that has not been published yet, and so I will just say look for an update on the Dales Gorge. So finally, in the same paper for these four formations, you can also estimate, here's the K estimates in all cases, and you can see as you go back in time, this is today, and Permian, Ordovician, Cryogenian, look at 70 already. So it starts at 50, we're back at 70, and then at the Dales Gorge, we're at 105 arc seconds per year rates. And then the G's are all fairly close to the starting values. So they do vary a bit, that's to be expected. And here's our Earth-Moon distances and length of day. You can see back at the Dales Gorge is estimating a 17.2 hour length of day at 2.465 billion years ago. So in conclusion, the proof of concept studies indicate that cyclostratigraphy can shed light important light on Earth-Moon dynamics problem for the past 2.5 billion years. And this was shown first by Myers and Malinverno, and now by Zhu et al. 2022. And at the same time, Lantink et al. Came out with a high-quality study in PNAS a couple of weeks ago. Short sections, 1 to 1.5 million year duration, are sufficient to obtain statistically constrained estimates of solar system GI and SI in the near future, the precession rate K, length of day, and Earth-Moon distance. And this was demonstrated originally by the time-opt MCMC technique by Myers and Malinverno. Having said that, there are other techniques in the works out there to tune the data different ways. At the moment, there's also an urgent need for orbital rotational solutions with adjustable parameters for tidal dissipation and dynamical ellipticity. This reminds me of what was provided by Lascar et al. In 1993, so that geologists were able to explore different values for tidal dissipation and dynamical ellipticity. Most recently, Zeeby and Lawrence have provided some new code that can be used to do a similar procedure. So in the end, there's strong promise for continuous. I sort of put this here. Here's the geologic timescale. I think there's quite a number of cyclostratigraphic sequences that can be exploited to provide high resolution empirical estimates of solar system fundamental secular frequencies, Earth precession rate, rotation rate, tidal dissipation, dynamical ellipticity perhaps, and Earth-Moon distance for billions of years into the geological past. So I just want to acknowledge my many friends and colleagues who've helped me and shared with me a passion for cyclostratigraphy now for more than 30 years. And real progress would not have been possible without financial support provided by currently the Heising-Simons Foundation and various Chinese funding agencies listed here, and in the past by the US National Science Foundation. So thank you very much.
Thank you very much, Linda. It was a really, really great talk, super informative. So remember, everyone, that now we are open for questions. Remember to type your name, type where are you watching from, and to send the questions to everyone. So in the meantime, I have actually a question, Linda, for you. I was thinking on, if you go back in the geological time, the geological record becomes way more incomplete. So how do you solve this problem with the cyclostratigraphy?
Well, there was an example that I showed early in the talk from the Cretaceous. And in the Aptian part of the section, geochronology has showed us that we were incorrect in our astrochronology. Right. Although it's sort of a different problem, is that we gave it more time than it should have had. So that's one problem. So we're going back to see what we did incorrectly, and we've already retuned it. But in terms of gaps, you're talking about gaps, and they're very common, of course. And the ODP goes around and they take multiple. They drill multiple holes at the same location just in case, just to fill in any holes that occur in the core, whether or not it's caused by drilling or by geological problems. It depends. You can't really see them.
Right.
You can't really see them. Sometimes you can see them. If there's a big unconformity, you can see it. But another example from the Albion in France. There was an attempt to try to develop a new cyclostratigraphic section in the south of France for the Albion and correlate it to the Piobico core that I showed you today. And this guy's very well known. He's spent many years trying to do it. He couldn't figure it out until he finished all the ammonites. And when he finished the ammonite analysis and the ammonite stratigraphy, he realized that 2 million years was missing. But you couldn't see it.
Right.
You couldn't see it in the outcrop. So the answer is hard work. We need more biostratigraphers.
Right.
You never know when you're going to run into a hiatus, because when you have a cycling section, okay, so
Yeah.
there's several
No,
ways.
and also I imagine that you need like super detailed sedimentology too.
Oh, absolutely, absolutely. You may, yeah, but yes. So there are a number of things. I mean, for example, with modern measurements, of gamma ray, for example, you're going up your Devonian sections,
Right.
and suddenly you see a step change. It's like, why did that step change happen? Is there's a lot of stuff missing that sort of might have given us a gradual trend,
right,
from one step to the next. And so we don't know the answer to that. And so caution has to be taken. So one thing that happens, so you could have nice cycling going along, and you wouldn't know it if you removed like 1 million years and then continued to cycle.
right,
Right.
Yeah, it's gonna be like the same signal, right?
You wouldn't see it unless it's cutting one of your 400,000 years and making it shorter, so suddenly it looks like a 200, or your 100s next to it look like 50s. You can, with great care and attention, you might be able to find these things. The one thing that
so we have. Yep, thank you very much. We have another question from David Fleischauer from the University of Münster in Germany.
Yeah.
So David said, first of all, thank you for your talk. He really enjoyed it. And the question is, the time-opt MCMC technique applies a single sedimentation rate to sequences that are sometimes more than 1 million years long. What would be your advice to deal with sequences that have clearly a change in the sedimentation rate, especially when you see a thinning in the precession cycles?
Okay, so time-opt MCMC is very specialized for determining these additional parameters. The G sub i's, soon also S sub i's with the G sub i's, together with K. But if you look at time-opt, in 2015. Steve Myers wrote a paper about time-opt where now you can input a linear change in sedimentation rate through the series, for example, or you could put in a hiatus, or there are different options you can put into the target to try to test for it. So to some extent that might be helpful. Otherwise you're stuck with sedimentation rate. Well, okay, so there are other techniques other than time-opt MCMC, or even time-opt, to try to estimate a time scale along a stratigraphic series. If you're lucky and you have a cyclostratigraphy that is carbonate rich, you might be able to, and shows carbonate cycles, you might be able to use carbonate content as a proxy or a measure for sedimentation rate variability. So we're still stuck. I mean, to a certain extent, I would always advise doing multiple types of tuning. If you need to do it by eye, just to get a handle on what you think you're seeing, you might see these cycles and they suddenly get very thin. And it's true, time-opt MC is not going to honor that. Now it can honor, if there's gradual sedimentation rate changes, you can use the E time-opt option to do a running time-opt analysis along long time series. And so that can change it. But of course, you're not going to do time up MCMC with every running window. That takes too long. So so you have to make choices.
Right. Cool. Thank you. We have another question from Gonzalo Calvo from Mallorca, Spain. And the question is, can we see in the geological record the recently discovered high-frequency astronomical climatic cycles like the solar system barycenter oscillation or the solar double dynamo cycle? That's the first one. And the second question is, do we have to go to the glaciological record only?
Oh no, we can go to Mars. No, no, of course we can. There are other things that have there are other materials that are available, such as ice, right? We have ice. I have a colleague now who is looking at Milankovitch cycles preserved and enhanced by metamorphism, Ross Mitchell, which is, I'm not surprised that he would be able to argue for that. Speleothems sometimes have long time scales, such as going through the last glacial cycle, 100,000 years, and so presumably it would record all of the Milankovitch cycles, in addition to all the high frequency variability one might expect,
right?
Such as millennial scale variability and so forth.
We have another question. Thank you. We have another question from Romain Boucher from Lausanne in Switzerland. He said, hello, Linda. Great talk. Thank you very much. I remember enjoying reading your 2013 paper in GSA Bulletin, in which you wrap up with the perspective of the cyclostratigraphy applications to other planets such as Mars. Where the research is going on this aspect? Any promising results?
Well, I mean, there's a solution for, there's an astronomical solution for Mars that is made available by Jacques Lascar. Thank you, Jacques. And it's thought that, so that the glaciations, I presume, are more are less what's the word, are closer to present day, but a majority of the very old sedimentary cycles or the formations are thought to be very old, Precambrian in age. As soon as we get one date, then we'll be ready to try to correlate. I think interplanetary correlation of Milankovitch cycles is on the horizon.
Wow, sounds like challenging.
Although we have the same problems, it's like it just depends on the material. Some of the material is just always moving around on the surface of Mars, so you have to have stuff that have to have material that is stable and indurate. It's not not moving, so not soft sand or anything like that. But there are there have been, including Jacques Lascar, who looked at the ice record on Mars, and then Kevin Lewis, who looked at the layering in, I guess it was Gale Crater. They have seen beautiful examples of patterns that seem to fit the astronomical solution provided by Jacques. Hard to say.
Definitely would be great to have like some other kind of record from Mars, but it's going to be hard.
That's right. So we need to
Okay.
core. We need to core. Big core.
Yeah, we need to ask Elon Musk.
Right.
uh, so, well, we have like the last question here, Linda. So before closing, we have another question from Gonzalo Calvo from Mallorca again. So how can we subtract tectonic phases from the geological record in order to see the astronomical cycles? Are the tectonic cycles completely different from the astronomical cycles?
Okay, so tectonic cycles, of course, are much longer scale. There was a period of time back in the 1980s and 1990s where it was thought that there could be, at least in the shallow marine records, you could have, episodic subsidence, sort of seismic, perhaps, episodic downdrops in the platforms, and that would cause, then that would fill up and it would look like a cycle, right? And so pulsating tectonics, and that could be on the scale of molecular cyclicity, 20,000 years, 50,000 years, and I suppose that's still possible, but it's never been. The whole thing was dropped, and in fact, platform carbonates, shallow marine platform carbonates, are under analyzed to this day because of their presumed, they're close to, accommodation limits. And so they will always seem to have incomplete records of cycles of any kind.
Right.
So otherwise tectonic cycles tend to be on, the million-year scale or longer. And it is true that, some of the long modulations in the astronomical parameters are on the same scale, 3 million years. I would say 3 million years and longer, without really knowing, would be a tectonic cycle that we would be looking for.
Right. So the different scale for sure.
Different scales usually, but there is overlap. So
okay.
So looking for long-term modulations is not as easy as we have made it out to be over the past 15 years.
Thank you very, very much, Linda, for being here today.
All right, thank you.
And thank you all for attending to this very interesting talk today. It was a very, very exciting topic. And don't forget to join us to the next SETS Online webinar, which is going to be next month because we have now changed to a monthly periodicity. And goodbye and see you next webinar.